Thank you. I'm what stands between you and lunch, so I'll try to keep it short. This is joint work with my colleagues at IBM Research and also my student Beomyeol, Jeon, who unfortunately could not be here due to visa issues. So on the bottom right, you see a puzzle of a house put together. Here is one more puzzle, incomplete. Can anyone guess what this puzzle is? Mona Lisa. It's fairly straightforward, right? It's not a complete puzzle. It's kind of sloppy, but it's okay. We can guess what it is. And that's kind of the theme underlying many of our techniques, as I'll describe over the next few slides. So this is a one-slide takeaway, right, for everyone. All right, so what's the problem we are solving? So the setting we have is an on-premises cluster or an on-prem cluster, as might be run inside a company or an organization. And this on-prem cluster has fixed total resources, a fixed number of machines, VMs, containers, replicas, what have you. And such consolidation of resources allows, across multiple jobs and users, allows the company to lower their capital expenses, the cost to buy machines, lower operational expenses, the cost to run the machines, also keep privacy-sensitive data local, and so on and so forth. So this exists already inside many, many companies. Now, given this, we want to be able to run multiple ML inference jobs, where each job essentially is a DNN model that is serving inference requests at some varying rate per second. So on the right side, you see over here, you see the variation of arrival patterns from one of the papers that we cite. Now, each of these jobs also has a latency target, also called as an SLO, or service level objective. I'll just refer to it as an SLO. This might be a 95th percentile latency or an average latency or what have you, it doesn't really matter. Now, predicting these time-varying arrival patterns is very hard. The dark lines on the right plot show the actual arrival pattern, and the dotted lines show the prediction, and it's always off by a little bit. But these jobs have very stringent latency requirements, which may be as low as a few milliseconds for arrival prediction, content moderation, to several hundreds of milliseconds for chatbot responses, and so on and so forth. Because it's very hard to predict these latency variations, you cannot predict how much resources to give to each job to satisfy the SLOs. And that means jobs are often over-provisioned, which means that they're given far more resources quite close to the peak, and that leads to more money invested in these clusters. So our problem here is we need to be able to auto-scale each job that is resident within the cluster. We have a multi-tenant setup, and give each job just enough resources to always satisfy its SLOs, even as the workload varies over time. Of course, there's been a lot of work in this direction over years and decades. Some work gives equal or fair resources to all the jobs. This, of course, doesn't work when jobs have different SLO requirements and different internal characteristics. More recently, some ML autoscalers have emerged, some of which are listed on this slide. A lot of these, unfortunately, assume unlimited resources, such as might be present in an AWS cloud or Microsoft Azure or Google Cloud. That doesn't apply to us directly because we have constrained limited resources. Nevertheless, we adapt some of those and use them to compare as baselines. Also, many of these techniques focus on only one job at a time, and they miss many of these cross-job optimization opportunities. A bit more recent work looks at multi-tenant scheduling, applicable to both microservices and inference scaling. This unfortunately uses techniques that are too slow to adapt. Our SLOs are orders of hundreds of milliseconds, and we cannot take minutes or tens of seconds or minutes to adapt. And this on the right side, there is a plot that shows the SLO violation rate of the system called Cilantro, which we compare against. And the SLO violation rate is essentially the percentage of requests that miss their SLO. So you can see that this is the most highly optimized version of that system. It's about 80% SLO violation rate. Compared to that, our system is a much lower SLO violation rate. And over the next few slides, I'll describe to you what the secret sauces are here. So again, the setup here is we have a fixed size cluster with multiple ML inference jobs, and each job has an SLO. The SLO may be different for different jobs, maybe wildly different. We have to address three questions. The first question is, how do you abstract the SLO into some kind of a function so that we can run it into some optimizer optimization package? Second, how do you predict the workload of each job? As you saw, this is very hard because it's hard to predict accurate workloads. And third, once you know the workload, how do you decide how much resources to give to each job quickly and in ways that are not short-sighted, that are not myopic, that are a little bit medium-term. So we address the first one by auto-distilling SLOs into utility functions, both for the job and then eventually for the cluster. We predict workloads by using probabilistic prediction, and we make auto-scaling decisions by several steps of optimizations and several relaxations. Again, remember the Mona Lisa incomplete puzzle I showed you? That's what underlies the philosophy under our approaches to Q2 and Q3, which is we use slopification or relaxation. And again, I'll say more about this over the next few slides. So let's look at the 4 building blocks of Faro. The first building block is abstracting the SLO into utility function. We have a job here that has a 500 millisecond latency, maybe it's tail latency. If the job is satisfying all its requests within the latency, it has a utility of 1. Otherwise, it has a utility of 0. And so we want the job to be close to 1. Of course, jobs may have different requests satisfying different latencies, and so utilities might be somewhere between 0 and 1. This can be represented by a step function. And once you have the utility functions for each job, we can calculate the cluster-wide utility, and this can be set by the cluster administrator. The cluster administrator might be trying to, for instance, maximize the sum of all utilities. That's Faro sum metric. If you have job priorities, you can add them on, as is shown by the pi multiplicand there. Or the cluster administrator may want to optimize fairness, or the difference between the max and the min utilities of any job, or you can combine the two. Now, these cluster metrics only account for requests that are actually satisfied. Some requests may be dropped because of out-of-memory errors and overfull queues and so on and so forth. So we also have penalty variants for each of those cluster utility functions, where we extract the penalty from Amazon Web Services SLA table. So for instance, if your job is satisfying between 95% and 99% of requests, with the other requests getting dropped, then we use a penalty of 25% or 0.25 in there. And that gives us penalty variance as well. So as a cluster administrator, you would choose one of these penalty functions for your cluster. Now, the penalty functions are nice because now we can take them and plug them directly into an optimization package. And I'll come to that in a little bit. The second building block is latency estimation. Now, one of the nice things about DNN inference is that past work has shown that arrival patterns are generally Poisson distributed, and the inference times per request are generally fairly predictable. We don't need this for our evaluation. Evaluation is with arbitrary workloads, but we can use this in our design. Specifically, we use an MDC queuing model. M is for Poisson arrival, D is for a fixed processing time, and C is the number of servers. Just using a very simple model itself gives us a 20% reduction in the number of replicas required to satisfy SLOs compared to existing work that assumes upper bounds. But there are challenges. It's not straightforward, especially when you have unstable queues, when the latency might go to infinity, and this happens when the arrival rate exceeds the processing rate itself. Again, I'll come back to this in a little bit. We have to solve this problem. Finally, to assign resources to each job, you have to take into account several aspects, including, but not limited to, the cold start overhead. Cold start overheads for jobs may be tens of seconds, and this exceeds the latency. So we need to use some kind of an optimization function to capture all of this and our cluster utility function. And so we end up using a proactive auto-scaling package called nhits, and this is after trying out several packages that are very robust and very mature. nhits is a preferable alternative because it's faster than other approaches, such as ARMA that was used in Cilantro. It uses less compute resources, so it's cheap and efficient, and it has better prediction quality than Mark's LSTM and Cocktail's Deep AR, as is shown by the root mean square errors on that table here, and nhits has the lowest root mean square error. So we use nhits. All right. So once you have the cluster objective function, we can input them to one of these packages. These are very well-known packages for SLS-QP. That's least square, Kobila is linear approximation, D is differential evolution. We can input them. Unfortunately, these packages are either very slow, like DE, which is quite slow, or they're quite far from optimal. So you want your technique to be somewhere to the top left, fast as well as close to optimal. Why are they so slow? Why are they so hard to solve? Well, the issue here is that you have what are called as plateaus in the search space of the optimization package itself, inside, while it's trying to solve the equation. A plateau is a flat region in the search space where nearby local search points return the same value, so you don't know which direction to turn. It's kind of you being lost in a big sea of snow and everything is white and you don't know which direction is the city. That's what that looks like here. Of course, we can do a global optimization, but that would be computationally a lot more expensive. We don't have time to do that because we have to satisfy these very short SLOs. So in our case, the plateau functions arise from the per job step utility function that gives you this steep drop and the step penalty functions as well. So we need to relax these plateau functions into non-plateau functions, and this is our first relaxation. Given the per job step utility function, we can, instead of having a vertical drop, we can write an inverse utility function that gives you the dotted line there. And that's kind of sort of like the SLO, it's okay. And it eliminates that vertical drop. If you have a penalty function that has a stepwise, that has multiple steps, we can use a linear approximation, and that eliminates the step and makes it differentiable as well. Is that sufficient? Well, it eliminates the vertical drop, but it still keeps the plateau at the point where the queues are going to be unstable. This is where the utility is 0, right? So this comes back to the earlier issue that I talked about with the MDC, where unstable queues are problematic. The trick we use here is to estimate the latency under an unstable queue as penalized latency under a stable queue. We use the same penalty function. And the penalty we estimate is proportional to the queue growth rate as opposed to the size of the queue. This is the queue growth rate itself. More equations about this are in the paper. I don't want to have equations on the slide. And essentially, the nutshell here is that this differentiates how fast the queue grows as opposed to just the queue size itself. And that eliminates this plateau as well and makes it, again, smoother. With this, we can input these non-plateau functions, these relaxed functions into these optimizers, and we move up closer to the top left to give us fast and close to optimal solutions. The second issue is that when you have a large number of jobs, it takes too long to calculate the solution, and also the quality of the solution degrades. The approach we use here, again, is to randomly cluster jobs and then use the solver in a hierarchical way across all groups and then also within each group. And it turns out that just using G equals 10 groups suffices to reduce the computation time by 64x and allows us to scale to hundreds of jobs. So we use G equals 10 in all our experiments. The last challenge is predicting the workload itself. The black line here shows for the Azure function one-day trace using n hits. The black line shows the actual arrival pattern. The blue line, somewhere in the middle there, shows the predicted. So anytime whenever you give resources based on that blue line, the predicted, you're in trouble because anytime the black line goes above the blue line, you're going to miss your SLOs because you don't have enough resources to satisfy all your requests. So what we do instead is we calculate windows. We calculate probability distributions. So the right plot shows the P20, P80 prediction. That's the pink bar. And the blue bar, which is the P30, P70 prediction. And then we can input these distributions directly into the n-hits package. You can use any other package as well. They pretty much accommodate distributions. And that allows the package itself to calculate a solution that lowers SLO violations. Putting these together, Faro first abstracts the SLOs into utility functions for each job, and then for the cluster itself, decided by the administrator cluster function. Then we use the cluster level optimization function that I've just described via relaxed per job utility functions. And then finally, when decisions are made to give resources to each job may have been given resources slightly more than it needs to satisfy its SLO. So we shrink each job additively, replica by replica, until it just satisfies its SLO. That's called as shrinking. That's the third stage. Of course, some of this might be slightly heavier weight than we intended it to be, so you don't want to be running this every 10 seconds. We run this at a medium-term scale every 5 minutes an hour setting. This is a proactive Faro autoscaler. We also run a short-term autoscaler that runs every 10 seconds that only additively increases and decreases replicas whenever SLOs get violated and satisfies per job. Okay? So both of those work in tandem with each other. Faro is integrated with the raceserve and runs over Kubernetes. I'm going to describe just a sliver of the experimental results. We compare against 4 baselines: fair share, which gives equal resources to all jobs; one shot that scales replicas based on per job based on the proportional to the latency; additive increase, additive decrease, which captures systems like SWAM, which reactively increment and decrement based on the target latency; and then Mark Cocktail Barista, which, remember, are systems that are intended only for settings with infinite resources, but at the heart of them, they rely on max throughput per job, and that's kind of what we abstract and implement in our system to compare it against as a baseline. I'm going to describe only smaller scale experiments. The paper contains larger scale experiments. Here we have 10 jobs with the top 9 Azure function one-day traces and the Twitter one-day trace. We have 2 clusters. The cluster with size 36 replicas in total is enough to satisfy our SLOs. The cluster with 32 replicas is oversubscribed, meaning it's going to miss some SLOs. Lower is better. We calculate 2 metrics. On the left side of each plot is the lost cluster utility. Lower is better. This is the amount of utility lost across all the jobs in the cluster. On the right side of each plot is the cluster SLO violation rate. Lower is again better. In both of these cases, the oversubscribed and the regular cluster, FARO gives 1.7x to 9x less average utility loss and lowers SLO violations by 2.3x to 12.3x. What about fairness? Again, lower is better here. This is average lost utility. The competitors, the baselines they have wider candlestick bars, which means that the SLO violation of the best job and the worst job are kind of far from each other. Compared to that, the FARO variants are a lot more tighter and also to the left. The FARO variants outperform the baselines on over-cluster utility. We also wrote a simulation. We did not just do deployments, we also wrote a simulation, and we matched the simulation with the deployment so that we can then scale the simulation to much larger cluster sizes than the deployment allows. We measured the difference in performance and accuracy between the simulation and the deployment, and it's about 9.6%. Based on that, we're able to do larger scale experiments with up to hundreds of replicas, and the nutshell of this is that the FARO sum and FARO fair variants perform the best overall. FARO sum is slightly better when you have oversubscribed, when you have limited resources. FARO fair is slightly better when you have sufficient resources. But more or less, they perform similarly. So wrapping up, existing ML inference autoscalers focus on a single job under unlimited resources. And when they look at multi-tenancy, they are too slow to adapt. FARO brings a solution by sloppifying and relaxing several components of the design, by predicting workloads sloppily using probability distributions, by converting plateau functions into non-plateau functions, and then the hierarchical optimization to scale to larger number of jobs. And this gives us 2.3x to 12.3x fewer SLO violations compared to the baselines. And the code for FARO is available at the link at the bottom of the slide. Thank you.